Precalculus, lesson 12.6, the binomial theorem. This is something that shows up a bunch in probability, has some really practical uses in probability, and then also because of that kind of spills over into statistics. So this is 12.6, the binomial theorem. And all right, so let's just say we have something like x plus y squared. Okay, well, we can expand that to x squared plus 2xy plus y squared. And I guess even if I take a step back, here, let me grab my little lasso selection tool here. Oh, that was it there. I'm going to scooch this down just a little bit to leave room for two things above it. How about x plus y to the first power? Well, that's just x plus y. How about x plus y to the 0th power? Well, that's just 1. Okay? And then, we could continue this going to like x plus y cubed, et cetera, et cetera, et cetera. Well, it turns out there are certain patterns that are going on that we can draw from to expand, so that if instead of x plus y cubed, we were dealing with something like x plus y to the 7th, that could get kind of tedious to start multiplying out by hand. So one thing that is useful here is something called Pascal's triangle. Pascal's triangle. Okay? And it looks like this. It has a 1, and then a 1 and a 1. And you keep going out in diagonals, and if you kind of view it as if there's zeros along the outside as well, which you don't have to, I'm just leaving them here for just a split second, that each number is the sum of the numbers above to the left and above to the right in the row above it. So if we look right here, for example, we do 0 plus 1, which just gives us another 1. Okay, oh, let me erase that other part of red. So that just gives us another 1. All right, so that's part of what's going on with the 1s all along the outside. But then in the middle here, we have 1 plus 1, that's 2. Then here, we have another 1 on the outside, and then a 1 plus 2, that's 3. 2 plus 1, that's 3, and then a 1 on the outside. And we continue that, we have 1, 4, 6, 4, 1. And then we'd have 1, 5, 10, 10, 5, 1. And then 1, 6, 15, 20, 15, 6, 1. And I'll do one more row here. 1, 7, why am I? 21, 35, 35, 21, 7, 1. Okay, well, these rows correspond to the coefficients, where if what we have is a binomial, so again, a binomial, a two-termed expression, right? In this case, we're represented as x plus y, but we could be talking about the coefficients of any binomial that we're raising to some power, where the powers that we're dealing with, this is the 0th power, this is the first power, oops, 1th, this is the first power, this is the second power, this is the third power, 4th, 5th, 6th, and 7th. So notice up above, when we did x plus y to the 0th, we just got a 1. In other words, we have a coefficient of 1. And you could say technically we have 1 x to the 0th, y to the 0th. And then the x plus y, you could say we technically have 1 x to the first plus 1 y to the first. And then the x plus y squared, we have 1x squared plus 2x to the first, y to the first, plus 1 y squared. So notice the coefficients that we have going on. For the 0th power, we just had a constant of 1, and that's that 1 there. And then we have a 1 and a 1 referring to the 1x squared, or 1x plus 1y. And 1, 2, 1, we have 1x squared plus 2xy plus 1y squared, etc. So if we wanted to expand that to the x plus y to the 7th that I referenced earlier, this row right here gives us the coefficients that we would have. But then that still raises the question, what about the exponents? What about the powers of x and y? Well, two things to note. We start out, in this case, with the 7th, we would start out with a 1. If I just go ahead and write all of the values here to begin with, we would have a 1, x to the 7th, y to the 0th. Now, we usually just write that as x to the 7th. But if I show all of the pieces of what's going on here, plus, now my second coefficient there is 7, so plus 7, x to the 6th, y to the 1st, plus the next coefficient, 21, x to the 5th, y squared. All right, so you probably see the pattern that we start with the first term to the full exponent of whatever is the overall power that we're dealing with. So if we're raising the binomial to the 7th power, it's the first term of the binomial to the 7th. And then from there, in this case the x's drop down 1 each term, and the y exponent increases 1 each term. And the other thing to note is that the sum of the exponents always adds up to the same thing that the overall power is that you're dealing with. So in this case, 5 plus 2 is 7, 6 plus 1 is 7, 7 plus 0 is 7, etc. So we could say that like this one right here would be 35. Well, if we start with y to the 0th, then 1, 2, 3, 4, y to the 4th. And because of the sum of the exponents needs to be 7 here, then this would be x cubed y to the 4th. Okay? So that's using Pascal's triangle. There are all sorts of cool properties of Pascal's triangle as well, and some of them involve Fibonacci numbers showing up. Some of them involve things involving like the diagonals and hockey stick shapes and things like that. But I'll leave that for you to look up on your own if you want to, which probably both of you are a little too busy if you're interested at all anyway, so that's fine. Let's see. Okay. Let's do one example, though, where you have things other than just x and just y inside the parentheses. So let's say something like use Pascal's, that should be a capital P, use Pascal's triangle to expand. And let's say we have this. What if we had 2x minus 5y to the 6th? Okay, now here's where you have to be careful with putting stuff in parentheses. So we'll be using this row here. That's our to the 6th power. And it's easy to identify which row is for the 6th power because of the second coefficient. The second coefficient always correlates to which power you're dealing with. Oops, sorry, I meant black there. Okay? So we would have a 1, which I'm not going to bother writing that. 2x to the 6th. The 2 has to go in parentheses because the 2 you're raising to the 6th power. And then the parentheses also end up making a difference here because we have a negative 5y. So then we have that, and then plus 6 times 2x, drop the power down 1, and add a negative 5y to the first. And then plus, now we have a 15. 15 times 2x, what am I at now, to the 4th, times a negative 5y squared plus, and I have a 20 now, 20 times 2x cubed times negative 5y cubed. And I'm going to stop there. But I am going to go ahead and multiply these out. So 2 to the 6th, let's see, 2 to the 3rd is 8. Oh, I grab my calculator and I have it in some weird mode. Let me see if I can get it back to that. Nope. What am I in here? Oh, I know what happened. My almost 1-year-old Molly was playing around with this the other day, or actually, I think just this morning, and she must have hit some button and switched it over to something. Okay, is it going to be in? See, I'm trying setup, and it has like some third degree. No, it has a cubic polynomial is greater than or equal to 0. Oh, that must be in the solving thing. Nope. Sorry if I can't. Ah, there we go. Okay. All right, so this is 64 x to the 6th. This is going to become a minus because I have that negative 5y hanging out there. So I'm going to do 6 times 2 to the 5th times 5. And it's going to become minus 960 x to the 5th y. And it's going to become a plus because my negative y term is being squared. So now I have 15 times 2 to the 4th times a y squared, or 5 squared, I mean, and that is 6,000 plus 6,000 x to the 4th y squared, and then another minus, and this is going to be 20 times 2 cubed times 5 cubed, and that is a 20,000, so minus 20,000 x cubed y cubed, and you could do the other few terms from there. Okay, so that's that. Pascal's triangle, though, can get a little tedious when you're dealing with even higher powers, and also when you are wanting just one particular term of what you're dealing with. So that's where we have a formula that is better, and we can represent the entire thing using sigma notation like this. And this would be, this is more of the binomial theorem. Would look like this, that x plus y to the nth power is equal to the sum from n equals 0. I'm sorry, from r equals 0 is what I want. From r equals 0 to n of n factorial over r factorial times n minus r factorial. And we have an x to the n minus r, y to the rth. All right. It might look kind of daunting, but it's not that bad. So if we're starting with r equals 0, then our first term is, and let's just say n is 8. Let's just say, so we have, let's just say we have x plus y to the 8th, okay? So then that's the sum of all of this, okay? So then the first term, we're going to use r equals 0, and n is 8 the whole time. So this is 8 factorial. I'll explain what's going on with this coefficient here in just a second. Times, now we're using r is 0 first, so that's 0 factorial times 8 minus 0 is 8 times 8 factorial times x to the 8 minus 0, or just 8, y to the 0th. So we don't have a y term. Okay. Then sigma notation says do plus, and now let's kick r from being 0 up to being 1. So we still have 8 factorial over 1 factorial now, and then I don't need these parentheses here, but anyway, 8 minus 1 is 7, so now we have 7 factorial, x to the 7th, y to the 1st, plus, and we still have 8 factorial on top, but now it's over 2 factorial, 6 factorial, x to the 6th, y squared. Now check it out. The top of this part, okay? The top is always the overall power that you're dealing with. Here's the overall power we're dealing with, that 8 factorial, 8 factorial, 8 factorial, okay? Then the other thing to note is what's on the bottom are the two exponents that you're dealing with. This first term is x to the 8th, y to the 0th. We have a 0 and an 8 on bottom. This is the x to the 7th, y to the first term. We have a 1 factorial and a 7 factorial on the bottom. We have a 6 and a 2. We have a 6 and a 2. The order, because it's multiplication, it doesn't matter. All right? When we look at the chapter involving probability, we'll see this formula come up. And just a really quick explanation, what this formula is dealing with is it's dealing with how many different ways can you form collections of items out of a set of items. So in this case, it's kind of like pretending like you have a bag with 8 X's in it, and you're wanting to know, like for this one here, let's just say, oops, I didn't mean to, I forget sometimes that I'm on. All right, this one here. This formula is calculating if you have a bag of 8 X's and you want a group of 6 of them, how many different ways can you form a group of 6 X's out of 8 of them? And if we pretend that like, well, there's the first X, the second X, the third X, the fourth X, etc. It's like you could grab X's 1, 2, 3, 4, 5, and 6 and leave 7 and 8 in the bag. Or you could grab X's 1, 2, 3, 4, 5, and 7 and leave 6 and 8 in the bag. That's kind of what we're dealing with here. And how I like to calculate these is I like to do 8 factorial divided by 2 factorial divided by 6 factorial. It's just easier for me to do on my calculator. If you're using your TI-83 or TI-84, factorial is not super convenient to get to. You have to hit the math button and then hit the left arrow and then hit option 4 is what will take you there. On my little Casio scientific calculator here, factorial is a little bit easier to get to. It's shift x to the negative 1. So I would do 8 shift x to the negative 1. That gives me factorial divided by 2, because 2 factorial is just 2, divided by 6 factorial, and this is 28 is what that simplifies to be. Okay, so this could be a quicker tool, especially like if you know a particular term that you're dealing with. So let's just say we want the something like this. Find the middle term of 3x minus, I'll go with minus 5y again. Nah, let's switch it up. I'll do plus, I guess. No, let's keep it minus. Minus 4y to the 21st power. Okay, 21st power. What's going to be the middle term? Well, so 21st power will give us a total of, because we start with x to the 21st down to x to the 0th. Odd numbers are not going to have a middle term. I need to go with an even power to have a middle term. That's right. So let's just go x to the 20th. X to the 20th. Okay. So let's look here at like to the 6th. We have a total of 1, 2, 3, 4, 5, 6, 7. So which one is the middle? 1, 2, 3, 4. The fourth one is the middle. when is x to the 6. So it's like cut it in half and add 1, basically. So here, cut it in half and add 1. That's going to be the 11th that is in the middle. Wait, is that right? So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, you know what? I don't even need to worry about that. 19. You know why? I'm dealing with the y terms, the y exponents here. So the reason why I just realized I don't need to do all this, so we have, yeah, total of 21 of these things. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, the reason I realized I don't need to worry about like double checking my thinking there is because the middle term, the exponents are going to match. And so it's going to be an x to the 10th, y to the 10th. Okay? So because of that, I can just jump straight into what we have here is 20 factorial over the two exponents, 10 factorial times a 3x to the 10th times a negative 4y to the 10th. And let's do some simplifying. The 20 factorial divided by 10 factorial divided by 10 factorial is 184,756. And then 3 to the 10th. These are big numbers, but it's what I get for picking what I did. 59,049. This is times 59,049 x to the 10th, and then times 4 to the 10th, 1,104,8,576, y to the 10th. Multiply all these out. 1,84756 times 59049 times 1,048,576, and we get 1.144 times 10 to the 16th x to the 10th, y to the 10th. I'm doing some rounding there. Okay, so there you go. Would not have wanted to do that by hand, like multiplying this thing out again and again and again and again and again until I get it up to the 20th power. All right, that is the binomial theorem. Let me know if you have questions. Hope it goes well.